How do you graph the trigonometric functions? This is a lesson for students and teachers, created by Holly Young. Please visit my website at www.makingmathematicians.com. Well, if you wanted to graph the trigonometric functions, you can always start with an xy t-table. Pick some basic angle measures for x and start calculating the sine and cosine. Well, some angles like 15 degrees, you don't really know those if you just draw a regular triangle, but we know our 30, our 60, our 45, and we can start getting some values for them and putting it on a graph. But a better way is using Linguini. So now we're going to use Linguini Trig to figure out how to graph. Well, the big unit circle in front of you, you can see is broken down into common angles. And if we took that unit circle and stretched it out, it would be a long line with each of those angles marked out. So we have two of them because we have two graphs. We're going to have sine x and cosine x. So sine x is going to be our top graph and cosine x is going to be our bottom graph. Now, if we use the unit circle to help us, what we're going to do is we're first going to create a radii, or a radius of the circle. So we go ahead and take a piece of Linguini and we measure the radius. That radius is going to help us all the way around the circle, because that, when we pick an angle, we're going to figure out what its horizontal and vertical component is going to be. Here's the deal. No matter where you are on the unit circle, you can form a triangle. And using that triangle, for sine, we would use the opposite side over the hypotenuse. And for cosine, we'd use the adjacent side over the hypotenuse to find the cosine and sine of that angle measure x. The thing is that with a sine, it's opposite over hypotenuse. So the opposite side is going to show up as a vertical component. The cosine is the adjacent side, which shows up as the horizontal component. We can use those two components and break them apart into two separate graphs, and then take a look at how they show up. So when I use my radii, I can start out with 0 degrees. Well, if I look at 0 degrees, it doesn't make a triangle. It only is the little radius right there. There is no triangle. So I'm going to take a piece in Linguini and measure it and make it the same size as that radius, because really I only have a horizontal component. It's not going up in the air at all. There is no vertical component at 0. So if I make my horizontal component, that goes with cosine, because I'm going out horizontally. There is nothing for the vertical component, so that's going to show up as 0. Now, moving on, if we want to move up to our angle measures, the best way to do that is to label the common angles around the graph. So we're going to go every 15 degrees around the unit circle. You could also label with radians if you want, but sometimes it's easier to see it with degree measures, especially if that's what you've been studying with the triangle. So I labeled out my common angle measures on sine and the cosine graph. Well, let's look back again at our 15 degree. So if I put my radius matching a 15 degree angle and I measure the vertical component and I take the Linguini and mark it, and then what I'm going to do is cut it so it's the exact right size to be the complete vertical component of the triangle that'll be made with the radius at that point at 15 degrees on the unit circle. So once I cut it and put that in there, I'm going to have a vertical component. You can see it's kind of small, and I match it up on the edge of the Linguini right at the 15 degrees. I also have to make a horizontal component of that triangle, and I'm dropping a right triangle because that's what we know our trig values come from, is the right triangle. So that right angle is going to be formed by the vertical and horizontal component. So there I'm marking off my horizontal component. I'm going to cut it and put it back there. So I have both sides of the triangle. Now I'm going to keep my radius, which is my hypotenuse. I'm going to keep my radius, but I'm going to take my 15 degrees and think about it for a second. Here's my triangle. If I think of a basic 30, 60, 90, the triangle I know pretty well, I can mark off from the 30 degree side the opposite, the adjacent, and the hypotenuse. But since this is a unit circle, the hypotenuse is equal to 1. So if I do opposite over hypotenuse, sine 30 is just equal to the opposite side. Cosine of 30 is equal to just the adjacent side, because the hypotenuse is equal to 1. So since that radius is not going to be used because it's equal to 1, I'm going to take my vertical component and move it to be sine, because it's over 1 anyway, and that's going to match up with my 30 degrees. Then I'm going to take my horizontal component and put it with cosine, because the cosine matches the horizontal component, which is the adjacent side. So now I have a couple values going on here. I can move my radius up to 30 degrees, once again measuring the vertical component at 30 and measuring a horizontal component so I get that nice right triangle in there and figure out both sides, remembering of course that my radius is still equal to 1. So once I put the sides in and measure them and get them in there just right, each component, I can then look and put them on the graph. But you can see the triangle, even though the radius isn't changing, the triangle, the side lengths are changing. The vertical component's getting bigger and the horizontal component's getting smaller. So I add my vertical component to 30 degrees and I take my horizontal component and add it to my 30 degrees for cosine. I'm going to continue that around at 45 degrees, which we know is my 45, 45, 90 triangle. So I'm going to match up the sides for that one and make sure that I get my vertical and horizontal component set. Once I do that, look at those two components together. What's interesting is they're the same length. They should be. It's an isosceles right triangle. So at 45 degrees, those two lengths are exactly the same. Now I'm moving up to 60 and I'm going to find the sides of the triangle and put the vertical and horizontal component where they go. What you'll start to notice, even when I move to 75 degrees up there and put the vertical and horizontal component, is that a lot of the side lengths are showing up the same, as there's a lot of symmetry going around here. So if you think about this wisely, if you make the graph yourself, you'll start to realize you need a certain number of each type of cut. At 90 degrees, once again, there is no horizontal component. So we cut a radius and it goes up to a vertical component, but there is no horizontal. Now, on the left side, the horizontal component is negative, yet the vertical component is still positive because you went to the left of the origin. So the only way to show that is to take that horizontal component and make it go below the graph. So now the sine and cosine graph have a positive and a negative component. And as I'm moving the angle measures around, if you notice, the vertical component is shrinking, but it's still positive, while the horizontal component is to the left of 0. So it is negative and has to go below the 0 graph. I keep moving around in that second quadrant until I get all the way down to our angle measure of pi. At pi, once again, there's no vertical component, but there is a horizontal one. So that's why that radius poked out there at 180 degrees. Now, back in that third quadrant, whoa, both horizontal and vertical components are negative in quadrant 3. You're going down for vertical below the 0 in the y-axis, and you're going to the left of 0 in the x. So that means that both values are going to go below the 0 graph line into the negative region. Once again, there's a lot of symmetry between the side lengths of the triangles. So you can see that some side lengths are corresponding with similar lengths elsewhere, and a lot of symmetry in the graph as you're making it. Right, we're now at 270 degrees. Once again, it's a radius with 0 horizontal component, but a lot of vertical. So it comes out with 0 on that side. Now that you're in quadrant 4, the horizontal component is positive, but the vertical is negative. It's stretching down below the graph, whereas the horizontal one is to the right of 0. So notice the cosine graph is going above the axis, while the sine graph is still sitting below the axis. And we finish up that last angle measure at 360 degrees, which once again is a radius with no actual vertical component. So sine is going to be 0. And this could keep on going around. Well, now let's fill in the values that we don't see, because there's angle measures in between all of those, so that they would have linguini at those different sizes, and this would force a pattern. And we can see that these are curves. They're a curved pattern there. And let's see what we can figure out from examining some of the connections from the sign that we already know about sine and cosine. So some of the things we're going to look for is, well, let's look for common fraction lengths in comparison with our radius of unit 1. So what are some common things that we know about sine and cosine? Well, the first thing we're going to do is look for the ratio of 1/2. So I'm going to take a radius and I'm going to start comparing it to the linguini around and see there are some of these lengths that are almost exactly 1/2 the radius. So wherever they occur, I'm going to take them and color them in blue, just to look and see if there's any kind of symmetry there. And what I notice is I'm having a version of a reference angle of 30 degrees. And that's happening all over the sine graph. All of the reference angles of 30 degrees are happening to be 1/2. Well, that should make sense because when you do the sine of 30 degrees, you get 1/2. And we know that the hypotenuse is twice as big in a sine graph of 30 degrees. That's the 1√3:2 relationship. In the cosine graph, the lengths that are a half are happening at the 60 degrees. And that should make sense also because when you do adjacent over hypotenuse, you'll see that you're going to get 1/2. Other common angle fractions that we can look for are 3/4. And it looks like that the ones right to the right in sine, right around them at 45, are working, and the same thing's happening in cosine. It's all at the 45 reference angles that are going to be 3/4. Well, 3/4, that's not a common one we know. Yeah, well, it's kind of close to 0.70, which turns out to be 1/√2. 1/√2 or √2/2 is about 0.70, which is really close to 0.75. So we can actually use those common fractions to help us approximate stuff. So let's approximate the value of sine of 20 degrees without using a calculator, because that's really hard. We don't know that without a calculator. We have to use our calculator to get it. Well, 20 degrees is somewhere between 15 and our 30. It's about halfway in between. So if I look at those lengths compared to 0, the blue is a half. It looks like that 15 is about a fourth, or about 0.25. So I'd say 20 degrees is about 1/3. And it turns out about 0.33 is a really close estimation. It turns out to be about 0.34. So you can estimate that. Looking at the unit circle, what happens if we change the radius? What if the radius of that circle was 5 units long instead of 1? What would happen to the sine and cosine graphs if we change that? Well, interesting to see. How you can change that is it gets twice as, if it keeps getting bigger, let's just think of twice as big. Well, if that circle enlarged to twice as big on itself, it would completely, that radius would be twice as big. So instead, at the cosine, instead of being 1, it would be a length of 2. But still, at the 0 point, when you hit the radius, the other component would be 0. So it looks like it would just stretch the graph completely. Instead of going up to 1, it would go up to 2, but still back at 0 at pi, and down to -2. Now, that length that we talk about, that height, is called the amplitude of the graphs, and that relates to the radius of the unit circle. So it doesn't change anything else about the graph, it just stretches it up and down a little bit for height. And you can see it at some of the target spots, pi/2, 3π/2, etc. Well, what's the period of the sine and cosine graph? Well, what does period mean? It means how long does it take until it repeats? Well, if you went to the unit circle, and if you went all the way around the unit circle and started again, instead of calling it 15 degrees, you called it 375 degrees, you'd be right back where you started. So it looks like the period for both of these graphs is 2π, or 360 degrees, that they will completely repeat in that time frame. Let's see if we can use this information to draw cosecant and secant x around the sine and cosine graphs. If you want to draw a cosecant, for instance, what you want to do, of course, is 1/sine. So if you think about a sine value like 30 degrees is 1/2, if you want to do 1 divided by 1/2, that becomes 2. So at 30 degrees, cosecant is 2. If it was 1/3, the cosecant would be 3. If it was 1/4, the cosecant would be 4. But down at pi/2, when it's 1, the cosecant is 1. So how do those graphs relate? Well, they seem to be inverses of one another. So if we get to our graphs, we can start at that 1 value where it's the same, and then it starts increasing. And then same down at the negative value, it starts out at -1 and then starts decreasing. So those little looks like two parabolas going in opposite directions are cosecant, and then secant does the same thing versus cosine, that it looks about the same. What happens is you also get asymptotes because you have to worry about what happens when you get 1 over 0, which is undefined. The number's getting bigger and bigger. So you have to put in asymptotes there. And if I look at that graph, I can say, okay, well, they look like parabolas mapped around the original cosine or sine graphs. Well, what's the period of the secant and cosecant graphs? Well, it still takes them 2 pi to repeat because that's what it takes cosine and sine to repeat. So they would be the same. Another exploration is looking at the graph of tangent. What would tangent look like? Well, go back to its definition. Tangent is sine divided by cosine. So go to something like 30 degrees, grab its value from sine and cosine, and divide them and see what you get. Do that with a couple values and start plugging out what tangent looks like. What's its period? What does cotangent look like? It's a fun exploration. Thanks so much for viewing our film today on Linguini Trig. I hope you enjoyed it, and I hope you come back to makingmathematicians.com.